Section: Introduction. We're going to delve into the world of large language models, LLMs, which are trained on massive amounts of text data, often billions of tokens. As these models grow in size, they tend to perform better at tasks like answering questions without needing to refer to external sources. They can also generate more accurate factual statements. However, even the biggest models can sometimes fail, especially when dealing with less common or rarely occurring facts in their training data. When they get it wrong, they usually produce a plausible but incorrect response, a phenomenon we call hallucinations. These hallucinations can become even more problematic when the task involves generating multiple sentences or paragraphs due to something called exposure bias. The latest research in language modeling is looking beyond just predicting the next word and is focusing on the model's ability to reason. We can improve the model's performance in reasoning tasks by encouraging it to generate internal thoughts or reasoning chains before responding, and by allowing it to critique and revise its initial response. In this study, we're exploring how and when reasoning can be used to reduce these hallucinations. We've developed an approach called chain of verification, CoVe, which starts with an initial draft response, plans verification questions to check its work, and then systematically answers those questions to produce an improved, revised response. We've found that independent verification questions often provide more accurate facts than those in the original long answer, improving the overall response's correctness. We've tested this approach across a range of tasks, from list-based questions to closed-book QA and long-form text generation. We've proposed a joint approach for generating the entire verification chain from left to right, which improves performance and reduces hallucinations compared to the baseline language model. However, models that pay attention to existing hallucinations in their own generations tend to repeat the hallucinations. So, we've also introduced improvements with factored variants that separate the verification chain steps, focusing on which context is attended to. These factored variants have shown further performance gains across all tasks considered. Hallucination is a common problem in language model generations that appears across many tasks, from summarizing to open domain dialogue, and hasn't been resolved by simply increasing training data or model size. There are three main strategies for reducing hallucination: training time correction, generation time correction, and augmentation, tool use. In training time correction, we try to improve the raw generations of a language model by adjusting the model weights to decrease the probability of hallucinated generations. This can be done using reinforcement learning, contrastive learning, and other methods. In generation time correction, we make reasoning decisions on top of the base LLM to make them more reliable. For example, by considering the probabilities of the generated tokens. Multiple samples are drawn from the model to detect hallucinations. Hallucinations are identified using low confidence scores, and their correctness is checked through a validation procedure, mitigated, and then the generation is continued. A third approach is to use external tools to help mitigate hallucinations, rather than relying solely on the abilities of the language model itself. For example, retrieval augmented generation can decrease hallucinations by using factual documents for grounding or chain of thought verification. Other approaches include using tools for fact-checking, or linking to external documents with attribution. There are also several approaches that have been shown to improve results with extended reasoning steps by the system, such as chain of thought, deductive verification, and self-verification. The latter tries to predict the question given the answer for math problems, and use that as evidence that this is the correct solution. Our approach, chain of verification, CoVe, assumes access to a base LLM that, despite potentially being prone to hallucination, is capable of being prompted with general instructions in either a few-shot or zero-shot fashion. We assume that this language model, when suitably prompted, can both generate and execute a plan of how to verify itself in order to check its own work, and finally incorporate this analysis into an improved response. Our overall process, which we call chain of verification, CoVe, performs 4 core steps. 1. Generate baseline response. Given a query, generate the response using the LLM. 2. Plan verifications. Given both query and baseline response, generate a list of verification questions that could help to self-analyze if there are any mistakes in the original response. 3. Execute verifications. Answer each verification question in turn, and hence check the answer against the original response to check for inconsistencies or mistakes. 4. Generate final verified response. Given the discovered inconsistencies, if any, generate a revised response incorporating the verification results. Each of these steps is performed by prompting the same LLM in different ways to obtain the desired response. While steps 1, 2, and 4 can all be invoked with a single prompt, we investigate variations of step 3 including joint, two-step and factored versions. These variants either involve a single prompt, two prompts or else independent prompts per question, where more sophisticated decomposition can yield improved results. We describe these steps in more detail below. An overview of the approach is illustrated in Fig. CoVe, and in the appendix in Fig. CoVe 2. Section Summary. Large language models, LLMs, have shown improved performance in tasks like closed-book QA, but they can still generate factually incorrect responses, known as hallucinations, especially for lesser-known facts. To address this, we propose an approach called Chain of Verification, CoVe, that generates verification questions to check the initial response and systematically answers them to produce an improved revised response. By incorporating independent verification questions, we observe increased accuracy and reduced hallucinations across various tasks, such as list-based questions, closed-book QA, and long-form text generation. Section: Baseline Response. Let's break down the process of our model, CoVe, which aims to improve the quality of responses generated by a language model. Firstly, we have the baseline response. This is the initial response generated by the language model to a given query. It's a straightforward process where the model generates a response from left to right. This initial response serves as a benchmark that we aim to improve upon in our experiments. However, these baseline responses can sometimes contain inaccuracies or hallucinations, which CoVe aims to identify and correct in the following steps. Next, we have plan verifications. Here, the model generates a series of questions based on the original query and the baseline response. These questions are designed to test the factual accuracy of the baseline response. For instance, if the baseline response includes a statement about the Mexican-American War, a verification question might be, when did the Mexican-American War start and end? The model is free to phrase these questions in any way it chooses, and they don't have to closely match the original text. We generate these verification questions by providing the model with examples of responses and their corresponding verification questions. Then, we execute verifications. This involves answering the verification questions to check for any inaccuracies in the baseline response. We use the language model itself to answer these questions, rather than using external tools like search engines. We explore several methods of executing verifications, including joint, two-step, factored, and factor plus revise. In the joint method, the planning and execution stages are combined into a single step. The model is given examples that include both verification questions and their answers. This method doesn't require separate prompts for planning and execution. The two-step method separates the planning and execution stages. This helps to avoid repetition, a common issue with language models. The planning stage is based on the baseline response, while the execution stage only includes the verification questions, not the original response. The factored method involves answering each verification question independently. This approach avoids repetition and interference from the baseline response or other answer contexts. It can also handle more verification questions, as they don't all have to fit within a single context. However, this method requires more computational resources, as it involves running multiple prompts in parallel. Finally, the factor plus revise method involves cross-checking the answers to the verification questions against the original responses. This is done through an additional prompt, which allows the system to explicitly identify any inconsistencies. For example, if the baseline response mentioned that Texas was annexed by the U.S. in 1845, but a verification question revealed that Texas seceded from Mexico in 1836, this would be flagged as an inconsistency. Section Summary. The baseline response is generated using the LLM without any special techniques, serving as the starting point for improvement in the CoVe pipeline. CoVe aims to identify and correct hallucinations in the baseline response by generating verification questions to test the factual claims made. These verification questions are then answered using the LLM itself, and the answers are cross-checked with the baseline response to detect inconsistencies. Section. Final verified response. We're going to explain the final step of our process, which involves generating a refined response that takes into account all the previous steps, including the initial response and the answers to the verification questions. This is done through a final few-shot prompt. If we're using the factor plus revise method, we also include the results of the cross-check inconsistency detection. Now, let's talk about how we tested our method. We used a variety of benchmarks to see how well our method, CoVe, reduces hallucination, comparing it to several other methods. We used different types of tasks for our benchmarks. Some required a list of entities as an answer, while others required a longer, more detailed response. First, we tested CoVe using questions we generated automatically using the Wikidata API. These questions were in the form of, who are some professions who were born in city? The answers to these questions were a set of entities, which we obtained from the Wikidata knowledge base. We used a dataset of 56 test questions, each typically containing around 600 known entities. However, a language model usually produces a much shorter list. We used the precision metric to measure performance and also reported the average number of positive and negative entities produced. Next, we moved on to a more challenging task. We used the Quest dataset, which was created using Wikipedia category lists. We turned these category names into questions by simply adding, name some, at the beginning. We believe this task is more challenging due to the variety of questions, such as, name some Mexican animated horror films, or, name some endemic orchids of Vietnam. We gathered all examples in the dataset that didn't require logical operations to create a set of 55 test questions, each having around 8 answers. We used the same measurement methods as in the Wikidata task. We also tested our method on a reading comprehension benchmark, multi-span QA. This benchmark consists of questions that have multiple independent answers. We used a closed book setting, where we didn't provide any supporting documents. We only considered factoid-based questions, so that our base language model was more likely to be able to answer them. We used a test set of 418 questions with shorter answers per span, up to 3 tokens per item. We also tested CoVe on long-form text generation, specifically generating biographies. We used the benchmark proposed in a previous study. The model was simply prompted to generate a biography of a selected entity. We evaluated our method using the fact score metric, which uses a retrieval augmented language model to fact-check the response. We used Llama 65B, a strong open model, as our base language model and used greedy decoding for all models. As Llama 65B is not instruction fine-tuned, we used few-shot examples specific to each task to measure performance. This served as our main comparison point, which CoVe aims to improve upon. For CoVe, we compared different variants, particularly the joint and factored versions on all tasks. We also compared to Llama instruction fine-tuned models. We measured both zero-shot performance on the task, or zero-shot with chain of thought by adding, let's think step by step, to the zero-shot prompt. We found that the instruction fine-tuned models tend to generate unnecessary content when queried. This can be a problem for the list-based tasks. To deal with this, we added an extra line to our prompt. List only the answers separated by a comma. We also used an off-the-shelf NER model to extract the answers to further avoid this issue. For the long-form generation of biographies, we also compared to several existing model results, in particular InstructGPT, ChatGPT, and Perplexity AI. Section Summary. The final verified response is generated by taking into account all previous reasoning steps, the baseline response, and verification question-answer pairs. The CoVe model is evaluated on various benchmarks, including list-based questions, set generation tasks, reading comprehension, and long-form text generation. The performance of CoVe is compared to baselines, such as Llama 65B, and different variants of CoVe are tested on all tasks. The instruction fine-tuned models tend to generate extraneous content, but CoVe aims to improve upon this by using few-shot examples and verification. Section. Results. We aim to answer 2 main research questions in our study. 1. Can CoVe effectively decrease the rate of hallucinatory content produced by the language learning model, LLM? 2. Can CoVe be used to correct or eliminate incorrect outputs without reducing the amount of correct content? Our findings, based on 4 benchmark tasks, are as follows. CoVe significantly improves precision in tasks that require list-based answers. For instance, in the Wikidata task, CoVe more than doubles the precision from the Llama 65B few-shot baseline, from 17% to 36%. We also noticed a substantial decrease in the number of hallucinated answers, from 2.95 to 0.68, with only a minor reduction in the number of non-hallucinations, from 0.59 to 0.38. CoVe enhances performance in closed-book question answering (QA) tasks, as measured on multi-span QA. We observed a 23% improvement in F1 score over the few-shot baseline, from 0.39 to 0.48, with improvements in both precision and recall. CoVe also improves precision in long-form generation tasks. Here, we saw even larger gains than in the QA setting. The fact score increased by 28%, from 55.9 to 71.4, from the few-shot baseline, with only a minor reduction in the average number of facts provided, from 16.6 to 12.3. CoVe improves results for both rare and more frequent facts. We found that the few-shot baseline, which uses a pre-trained Llama model, outperforms Llama 2 Chat, an instruction-tuned model, across all tasks. The few-shot examples guide the model to produce outputs that align with the task expectations, while general instruction tuning tends to produce more hallucinations or incorrect outputs. Standard chain of thought, COT, prompting also fails to improve the results for these tasks. We observed a consistent performance improvement across all tasks when applying the factored CoVe approach compared to joint CoVe. For instance, in long-form generation, the FACT-SCORE improved from 60.8 to 63.7. The two-step approach also outperforms the joint approach, as tested on the Wikidata and Wiki category list tasks. In the long-form generation task, we also explored more sophisticated reasoning steps in the CoVe factor plus revise method, which explicitly cross-checks whether verification answers indicate an inconsistency. We saw large gains in the FACT-SCORE metric from this further explicit reasoning, from 63.7 to 71.4. This suggests that appropriate and explicit reasoning in LLMs can help reduce hallucinations. On the long-form generation task, our baseline few-shot Llama 65B is outperformed by the ChatGPT and Perplexity AI models in terms of the FACT-SCORE metric. However, applying CoVe to the baseline Llama 65B improves its performance above both ChatGPT and Perplexity AI, as well as outperforming InstructGPT. This is particularly impressive compared to Perplexity AI, a model that supports its facts with retrieval augmentation, whereas CoVe uses only the base language model itself with improved reasoning via deliberation, verification. In conclusion, our results support our hypothesis that verifying questions should not attend to the original baseline response, as they may be prone to repeating it. We also note that some models produce fewer overall facts than others, but the FACT-SCORE metric is normalized and hence comparable across models. Section summary. The study aimed to answer 2 research questions: whether CoVe can effectively reduce hallucinatory content produced by the LLM and if it can fix incorrect generations without decreasing correct content. The main findings showed that CoVe improves precision on list-based answer tasks, performance on closed-book QA, and precision on long-form generation. Additionally, the study found that instruction tuning and chain-of-thought prompting did not reduce hallucinations, while factored and two-step CoVe approaches improved performance. Further explicit reasoning in the CoVe factor plus revise method helped remove hallucinations, and CoVe-based Llama outperformed other models in terms of the FACT-SCORE metric. Section. Short-form verification questions are more accurately answered than long-form queries. We found that short, specific questions are answered more accurately than broad, long-form ones. When asked to provide a long-form response, language learning models, LLMs, tend to produce a number of incorrect or imagined responses. Interestingly, if we were to ask the LLM about these incorrect facts individually, it would often recognize them as wrong. This is evident in our Wikidata task, where only about 17% of the answers provided by the Llama few-shot baseline were correct when asked in a list-based format. However, when we asked about each fact individually, the accuracy jumped to around 70%. In our approach, which we call CoVe, the LLM generates verification questions based on the task at hand. We compared these LLM-generated questions to ones we created using a set formula to gauge their quality. For list-based questions, we replaced the LLM questions with simple yes/no questions like, does X answer the question? Where X represents elements in the answer. Our results, shown in the Wiki category task, revealed that the precision of rule-based verification questions was lower. We suspect this gap would be even larger for long-form generation, where the variety of necessary verification questions is greater, making LLM-based verification even more crucial. We also found that open-ended verification questions, where the expected answers are factual, outperform yes/no-based questions. We tested this by including the fact in the verification question and asking it in a yes/no format. Our findings, detailed in our results, show that yes/no questions perform worse for the factored version of CoVe. We've included some examples in the appendix where we found that the model tends to agree with facts in a yes/no question format, regardless of whether they are correct or not.